Okay. So, do you need a break or we can start, right? Yeah, we can start. Okay, cool. So I hope you all had a really productive week, thanks to Slack, right? So, no pings, no bosses for a while at least. And although I heard some people got a little bit panicked for a few minutes, but anyway. So, yeah, one thing we know from that is that distributed systems are hard, because it seems that the outage started off with one shard going down, and then it had some ripple effects, and that caused a cascading failures. So, yeah, again, it just reinforces what we already know. Distributed systems are hard. The problem is that the way we are testing has been the same, or roughly the same, for last 20 years, where most of our testing is. Yeah.
Speaking to both because of the AV.
Okay. Yeah. Most of the testing is still manual, whether we like it or not. That's what we still do, and a lot of even the automated testing is like few engineers writing some tests, and most of them are still following the old way of doing things. Single-threaded tests. Majority of them are unit tests, and the end-to-end tests are more or less a checklist item, because you don't do fault injections to verify if some node crashes or any of those. So how do we still build good distributed system? Because the world is still running on distributed system. We are just, by our own intuition, we have a like senior engineers or whatever, they architect and think about various scenarios and have a good design and assume it works, and hopefully if it's implemented correctly. And most of our testing is on the implementation, right, not on the design. So so that has some issues, because the design phase is still more or less manual. Manual in the sense, like, it's still same what we used to do 25 years ago. Long prose document. The format of design document has not changed a bit in the last 20 years, right? It's same prose document, ad hoc images. That's not suitable for any automated analysis. So we just rely on other people to review it and find bugs in the system, which leaves a lot of holes in the design. So today I'm going to talk about how to model these systems in a way where, for at least the distributed systems part, we should be able to model it much faster than the way we write traditional design documents. And then we should be able to validate its correctness and gain confidence in the system. So that's what I'm going to talk about today. So, by the way, I'm Jai Prabhakar Kadarkarai. I am the developer of FISBee. It's an open source formal verification tool, but more or less I'm now talking about it more as a distributed system modeling tool, not purely as formal methods, because no one likes formal methods. So the specification language is it's a Python-like modeling language. It generates the visualizations and run simulations. You can add assertions, both safety and liveness properties for model checking, and it also does performance modeling, so that you can get the performance parameters like latency or error rate or availability and so on. And also it generates automated test cases. So that way we can validate whether our implementation matches the design more or less automatically with only a minor input from the users. So to show, I'll start with a classic example like travel booking service. This is something that we all would have used, booking.com and other things, where we are designing a service where we want to book multiple entries in as part of an itinerary, like flights, hotels, rental cars, and the key constraint here is that the booking must be all or none. So either all the flights and the hotels should be successfully booked, or nothing is booked. So now partial bookings. So people who are familiar with this probably know that we do two-phase commit protocol, right, for this. How many of you are familiar with two-phase command? Okay, pretty much. Okay, so it's more like a rhetoric at this point, I guess. Maybe who don't know about two-phase command? Okay, wow, 2 people. Okay, so sounds good. So actually, yeah, that's one reason. Yeah, most formal methods folks also use this as an example. So it basically it happens in 2 phases. In the first phase, you do pre-auth. So you place a hold on the resource. So the coordinator, the booking service, sent like, okay, place this resource on hold for me to multiple participants, and they respond either yeah, accept it or reject. If one of them rejects, we say, okay, cancel the booking. Otherwise, we say, okay, committed. Yeah, that's the protocol on a high level. So to model it, just from this diagram itself, you should be able to know like who are all the actors in this model, or the actor model. Yeah, what roles? There are like 2, coordinator and participants, right? So to model it in FISB predominantly Python-like syntax, but again slightly different for the domain. So it starts off to define a role. It's similar to how you declare a class in Python. So instead of class, you just use a role keyword. So role coordinator, and we have another one participant. And here, if you see in the 2 phases, there are like the participant has to support 2 RPC calls. You have one for prepare or place hold, second one for finalizing the decision. So I'll start with the participant. So the action init defines it's more similar to a constructor, and again like Python. And how you define the field in Python is you use self dot that field name equal to the state. So it has so here I'm defining a status as a state for that role, and the place hold function, it's again here, since the participant is not in our control, we can just mark out, or most likely when you're implementing, we'll mark it out, right? Same way you can say that you at an abstract level, it is going to choose to vote either as accepted or aborted. So we just use a keyword any to use say accepted or aborted, and self.status equal to vote. So it persists its state whatever it decided for the transaction into for its status, and yeah, return the status. And the second RPC finalize is pretty again trivial. It just takes like sets the status of whatever it is passed on from the coordinator. And for coordinator, it's again it also again here we are modeling a single transaction. So instead of a map of a transaction ID to the status, we are just keeping a single status because it's a single transaction. So it also has a status as init, and checkout is an action that the actor supports. So as a first step, since again we are not doing a repeated transaction, so we have a precondition only in the init state. It has to go to the working. So that it and then for each of the participants, again same Python syntax, vote equal to p dot place hold, and if one of them aborted, finalize as aborted and return. Otherwise, finalize as committed. And for the second, for this, it's a finalize a helper method. So just say self dot status is decision, and for p in participants p dot finalize. Okay. So far, any questions for this? Okay. Yeah, and so now that we have defined both the actors, now the next step is to define the environment. Here again, I just need to say I need one coordinator and multiple participants. In this case, again, I'm declaring 2. Again, the body of the method is almost like Python. So anyone familiar with TLA plus or those know that, okay, this is much easier compared to the other formal methods. So that's it. So now we have modeled TLA, two-phase commit. So no, we don't need any other changes. Yeah. So again, to recap, I'll start showing the demo. But before that, I just want to recap. When you have a problem distributed system to model, the first step is define the roles and define the states. And how do you want to represent those states? Define the RPCs actions and actually implement that RPCs. The setup for the environment. followed by that again. In this example, so far I haven't added an assertion, but you can add assertions for safety and liveness properties. I'll get to that. Technically, without assertion also it is still useful because you can model and simulate what you want. So let's do a quick demo. So I copy pasted the same code. Is it visible for the folks at the, okay. Is it good? It's okay? More? Oops. Okay. Yeah, okay. Anyway, I didn't optimize the UI for a small screen, but anyway, I just copy pasted the same code, and I have some commented out lines. I'll get to that later. And I added one thing temporarily. I'm disabling the deadlocks. I'll show you again why. So yeah, so now when you run it, it should anyway, finally it got. So again, since we didn't have any assertion and all, it said yeah, everything completed successfully, and it has already generated the state space. Sorry, yeah. Okay. So here you can see like how the state transition happened. So for example, in this case, the coordinator started in the init phase, and the only action was checkout, and immediately it went to working state, like the first step. After that, there are two possibilities. The process could crash. So I'm just modeling that also automatically. And then in this case, you will see that once it crashed, there is no outgoing step. So that's technically a deadlock. So that's why I had to disable, so that we'll focus on more important parts. And then, other part, you can say, okay, what happens when that checkout flow continues, and you can actually explore the state diagram. The other, again, it also generates these block diagrams you would have normally written again automatically from this spec. You typically would draw these diagrams for your design doc, right? So this also comes off the shelf. And finally, more interesting part is, oops, can I reduce the screen size a little? Is it okay to some extent? Mm-hmm. Okay. Yeah. So now you can actually interactively explore how this spec works for various possible actions that can happen in the system. So in this case, again, since there is only one action, you can say check out, and if it crashes, it goes back. There is no other step. So again, when it started, it again changed the status from init to working. Now you can actually explore the next step is place hold on the first participant. There it again can choose between accepted or aborted, changing the status. So that way you can actually explore what happens, and the sequence diagram again would be generated automatically for you to include into your design doc, or you can actually explore if everything is working fine correctly, right? So because even when we are sharing design docs, usually people, one of the first questions, what happens in this scenario? Now we can say, oh, look, explore this. So that it saves time for both the sides. And typically in the design docs, we generally put one happy case, and at max, one like a failure case scenario, right? So now you can have exhaustive scenarios and explore it interactively. And yeah, in this case again, end, right? So now, so you have a question?
What sort of structures do you use to simulate each element in distributed systems?
Can you repeat what?
How do you simulate each element in distributed system and the communications between them?
Yeah, so it basically has an interpreter which generates the state space. So after that, it's a LTL logic similar to TLA plus to verify for liveness properties. But here the model checker is pretty much built in-house. So so it's a complete re-implementation of the model checker. And for the expression parsing and all, I'm using Starlark, which is a Python subset, which if you're familiar with Bazel, that's what it uses. So I just used it, so that way I can reuse make it more compatible with Python. So I wanted to make one change, since let's say So we notice that if the process crashed in between, like after some customer, some of the participant accepted, the customer, the participants will never know whether to keep the booking or not, right? By contract, they have to keep it forever. So we, for liveness perspective, it would be better if we can indicate that we should, let's say after a timeout, it should abort, right? So let's say we make a small naive implementation, I'm just commenting out so that it shows a bug. Okay, so yeah. Okay, yes. Okay, so it created again. I don't have any assertion, so you probably won't see it. You can explore it to see what could happen. For now, in the interest of time, I will actually add the assertion actually. So yeah, it shows that. So basically, the assertion is again like a Boolean function. All it has to return is true or false, as long as and always indicates it's a safety assertion or safety property. So the again body is Python code for P1 in participant. For each of the participant, if one of them is in committed and one in aborted, then it's actually a illegal state to be in. Otherwise, it's a valid state. So you can see that in this scenario. Okay, so what had happened is that the first one committed. Sorry, the screen is too small. So and once the commit happened, the timeout handler triggered, and then it reached the aborted state, and then it had so that led to one of them aborting and one committed. So and for but really speaking, like debugging is will be painful even with all this. So we have many different interfaces to show like what happened, like at what line things happen. In this particular case, you can see the thread, first thread completed with the first action, checkout action. The second thread started with a timeout action after everything got completed, and the state change here it changed from status committed to status aborted. Oops, sorry again. So here you can see the status changes from go ahead.
Sorry, this might be a little bit general, but what made you pick your own language or create your own sort of domain-specific language for this purpose? Like, why not use Python? What sort of does this give you, this extra syntax?
Yeah, actually, it also evolved in the first place, but the main reason it cannot be just Python interpreter is that I need to simulate the like a threading with the different semantics for this purpose, right? So I can show some more examples, but see, in again regular Python, if you have like a x equal to x plus 1, the semantics of concurrency is slightly different. Okay, whereas for this, I wanted to have a slightly different concurrency model. That way, it is not exactly that way we can keep the state space smaller. And and there are a few other things like So this way again for to debug the states, you have all the intermediate states and all the variables, so that way you should be able to debug the fault. And again, in this case, all we needed to do was make sure that if it is already committed, don't abort. But just curious if anyone can find if there is an issue with this. But sorry, the screen is too small, so you won't have a full picture. But anyway, I'll probably run it again. Yeah, it will have bugs. So in this particular case, okay, again. In this case, if it goes at a different thread interleavings, then it will expose that bug where okay, so maybe this view for it is better. So I need to have multiple views to understand. So in this particular case, what happened was the first thread reached the state where both of them accepted, both participants accepted, and in the second thread, the timeout started, it aborted, but there was a context switch that led to the first thread continuing to commit. So that so this kind of thread interleavings, again, it simulates to make sure that those scenarios are also tested. So we can identify those kind of bugs here. The okay, yeah. So I can fix it, but if so, again, we could add a few more preconditions here to reduce the. Okay, I think we probably can skip that part. So basic idea is the language is pretty simple enough that most people should be able to model without much formal methods background, and again in this case, how many of you are familiar with the TLA plus? I know you are. Okay. Oh wow, almost 10 to 15 people. Okay, and any other formal methods you guys are familiar with? P or
Formula, spin checker.
oh wow, okay. Yeah, that's an extreme one. And cock, like a proof, theorem provers as well. Okay, yeah. So in this case, I wanted to keep it more simple for normal software engineers to use. So I had to pick a lot of assumptions and that is suitable for distributed systems developer. And mostly I was starting, instead of thinking about it from a formal methods perspective and bringing it to the user, like what if we can make a modeling tool and then add assertions to it. So that way it made it a little bit easier and concise. So yeah, go on.
Sorry, this is probably because I'm very unfamiliar with formal methods, but I'm curious, like, what sort of guarantee, like, after it passes this checker, right? What guarantees do we have about the system? Like, how does it reassure me that things are working?
Yeah, no, it just reassures that your design is correct. Correct in the sense it matches the specification specification in the sense the assertions are these properties you defined, like usually deadlock, some of the liveness properties and safety properties. So and it also gives you a much more cleaner precise specification for the development team to actually look and when they implement, they can cross-reference. Because in a design document, again, it's a free-form text. Many times, I've seen it also. I ignore some case. Someone points out that, hey, look, did you think about this case? I'll see, nope, I didn't think about it, but I still update it and say, yeah, I thought about it, and I updated the reference, because who wants to admit that we didn't think about it, right? But the thing is that there are some who would have assumed that I already thought about it, right? So those kind of assumptions also happen, and worst thing about design documents is it is so static that no one wants to go back and update a old design document. If you want to make some changes, you always end up creating a new design document, and at that point you miss out on many of the assumptions that were baked in the previous design, right? So here, being a live executable specification, you can actually validate and continue to update. So that's a guarantee. But in addition to that, we can also generate the test cases based on this. So I'll go to that later. So far, do you have any questions about FISB specification language or anything? Yeah.
So is the expressiveness of this language the same as TLA plus, or is it like a subset or superset of?
See, both are Turing complete, so they are same. So it just that the TLA plus by itself doesn't have any threading concept or anything. They use very it's a low level math, basic prepositional logic. So that makes it creating, like, expressing sequence of steps means that you have to simulate like program counter, and if you want to simulate multiple threads, then again you need multiple program counters. It becomes much harder. Again, PlusCal is good for certain use case, but it also becomes complicated for much longer specification. So here I was trying out to be like so in a design doc also, many of these scenarios people express it as a pseudocode, right? So how close it is to the pseudocode is how I was looking at, and yeah.
So I'm wondering, what is your network model?
Which one?
What is the network model that you're using?
So in the like the by default the inter role communication is we are treating it like an RPC. So for intra role it is like just a helper function. So so which basically means that we actually have slides for it, but we also simulate message loss and yeah, partition, network partition, which is again a kind of a special case of message loss anyway, and node crashes and other things also.
I see.
Oh.
So like messages delivering out of order, stuff like that.
Yeah,
It's all covered.
yeah, that's all covered.
So I just had a question on the user interface. You only have like a couple of cases of self here, right? Just a very small enumerated list. What happens if you get into like very large cases of like dozens? What happens to your diagrams at that point? Can you like kind of like put an ellipsis there to kind of like skip over states, or like do you have any control of the output there?
On the diagram?
Yeah, the diagram.
So yeah, I'm still working on it. It's in yeah.
All right, fair enough.
So I want to get things like to work out of the box. I know TLA Plus many people are keep building their own custom version, but it takes a lot of effort for each model.
Mm-hmm.
So yeah, I want to get it to work for a bigger model.
Right.
So single biggest thing is actually removing some unnecessary details. So
Mm-hmm.
yeah. So in the open source version anyway, when you run it locally, it dumps all the state space. So if you want, you can obviously make the changes or build your own visualization. But ideally, I want it to be baked in. So yeah, since you asked about it, I just noticed that I don't have an example for multiple states, state variables. Let's say I'm just create a naive variable, okay? Let's say XYZ. So let's say in this case I'm declaring a second variable, and for now let me remove all the assertions so that I can demo the thread. So when a checkout action is called, now there will be two variables that are going to be updated. First one is status would be updated as usual, and in the second step the next variable. So in this case they are not updated atomically, so it's one after another. So which means it can be an observable state from a different thread or so, right? So yeah, when it started off, there are two variables. When one of them like this one happened, and the next step the second one updated. But if we want it to be, sometimes we want to update multiple variables in a single atomic action, right? So we just have to mark it as atomic. I think Promela has a similar syntax, but slightly again they use C style, so curly braces, but otherwise it's similar. So now when this so there won't be any context switching, or there won't be an yield point between these two changes. So so here like both would be updated at once, yeah, so both gets updated, so there is no yield points in between. Similarly and again, if you since you mentioned about draft protocol and all, like Diego and Kara actually very clearly specified which variables should be durable, which ones are ephemeral and all, right? So you can actually specify something like this here itself, just with the, by default all the variables are durable, all the state variables, because that's what most things we model that seem to be logical. But if you want to mark any of them as ephemeral, I hope my spelling is correct. Let's say like I want the this variable to be, or this field to be an ephemeral variable. Now it would basically, in this case, it's going to simulate the process crash as well, and in that case the since variable is the ephemeral one, it goes back to the old one. Let's say I'll for my own. So now when it started, both of them got updated. Now let us say the role this one crashed, so the ephemeral role goes back to the initial one. So that way we could start simulating the process crashes as also. So I think in TLA plus you still have to manually say which ones are or what happens when restart or process restarts and all. So here the goal again is the model should reflect how easy how close we are planning to implement. So with TLA plus the mapping between the implementation and design is a little complex. So many times it's like you won't even know how whether they are actually there's a one-to-one mapping or not. So that's one another feature. So okay, let me do like just quick recap of like when you are starting to model. So this is what I noticed. People who tried FISB like during the tutorial, oh yeah, everything seems simple, but when they start on the first model, they find it really hard. Actually, the getting started was almost always harder. So yeah, I needed to list out the exact steps, find out the roles that you need, then states. Getting the first two things actually makes the rest of the things flow through easily. So after that, it's like it's easy. You will notice that once you define the state, okay, yeah, I needed this RPC. These are the actions, and implementing them becomes trivial. So from then on, and so we model the non-determinism. Like typically, there are true non-determinism, which usually we don't model it during this. In distributed system for some reason, but sometimes like random choices we still have to do it. Other one is IO operations are usually modeled as random sorry, non-determinism, and abstraction is another area. Even though it can be deterministic, many times we model it as non-determinism. In this case, like we even if the participants would have the deterministic algorithm for accepting versus aborting, we still can say, okay, yeah, okay, we can use just abstraction to simplify that part. It reduces the state space and the complexity of the model, and it's very similar to how we would generally do mocks in DY. Another source of non-determinism is concurrency. So we saw about any keyword. I'll probably skip. Oh yeah, actually this is. So this is the only noticeable addition to the language, which makes it not Python actually. So, but we saw the basic version, right? Any of collection, and we could add conditions to it, like that way, how we can filter out how we choose the element from that collection. This is similar to some math guys would know, like there exists an element such that, so that. That is that if condition part, and any by definition keyword actually picks, it defines select any arbitrary element, but it doesn't say it should be fair or not. So we can define it. Sometimes we want it to be a fair choice to simulate a true random. So you can add that fairness condition. Yeah, and these are the faults. Right now it is modeled automatically, like the message loss, partition, crash, and process crash, and node failure. The thread crash and process crash, you probably would have noticed the difference. Thread crash means that only that sequence would be lost, but the state remains, including the like a global ephemeral state. But in the process crash, that also would be wiped out. So right now it doesn't model data corruption or a node's permanent mainly data corruption and a few other types of failures. And I think yeah, I'll probably skip and go to autonomous testing for just a couple of minutes. So if you look at the typical testing, that how we write unit tests or any type of test, the first step is we initialize the system like what the current state should be. Like it could be like starting from an empty list or a certain state, and then they perform the action. If you are sometimes if you want to test a clear function of a list, you will be calling that, right? So initially populating with a certain number of elements and calling that action. Finally, it would be the assert, either asserting on the return values or the new state. So this to get this kind of test, right? So the state graph you would have seen, right? So it has all this information already. So since we have that information, we could actually do an extensive tests. Oops, there's a typo. Oh no. We can be unlike a manually written automated test, where we typically we usually have only a few test cases, right? Here we could go pretty exhaustively, and in addition to that, we also do concurrency testing, which is typically not done in most unit tests, because like if you have multiple sequence of operations in two threads, it's very hard to even make an assertion that what the final state should be. So instead, since we have the full specification, we generate the trace, and from the trace we check whether the trace matches one of the things in the model. So it's again an NP hard problem. So but for most of this scenario it works. So we tested it on some open source project, and it found a lot of concurrency bugs, even though they had a very good test coverage. So I think, yep. Yeah, I think that's it. So do you have any questions? Yeah.
This is really cool. It looks a lot. Thank you. This is really cool. It looks a lot easier to learn for me than something like Daphne, Pascal, or Coq. One question I had, is the execution designed to be state space exhaustive, or like a simulation that just runs indefinitely?
So it has, the question is, do you have exhaustive model checking or simulations? Right? So we have both. By default, it does exhaustive model checking. So, for context, exhaustive model checking, basically we do BFS and check for every possible state, and keeping track of which ones are already visited and all. In the simulation mode, we don't keep track of anything. We just can randomly choose the next step and execute. The biggest advantage of simulation is it can be parallelized easily. So since there is no we are not tracking any states, so it's embarrassingly parallel. So that's why many people, most likely you guys also would have used simulations, even though most people start with model checking, basic model checking, and then say, okay, now we probably need simulations. So so right now FISB has both the options, but I'm now in the UI, it's only like the exhaustive model checking. I'm now changing it to simulations, so in a few weeks I'll change it, because I see that for any real problem, simulation works better, and it actually finds bugs faster than exhaustive model checking, which I didn't realize that would be the case until I started tracking some numbers.
Thank you.
Yeah. Oh, he asked a question. Okay, go ahead.
Thank you. Yeah, I was curious if you had any insight onto why standard test libraries in Python like PyTest don't have good support for simulation-based concurrency testing currently.
Yeah, honestly speaking, I didn't explore that at all. That's a real thing, because I was mostly using TLA plus, and then when I was showing people, I couldn't even convince anyone to review the spec. So that I'm not sure if you guys faced the similar issue. So getting someone to review it is also hard. So then I thought, okay, I'll do it, and I never even I was never a Python guy, so I never even looked at Python and that before that. But then. Yeah, it would be a long answer, but yeah, but honestly, I didn't look at it before. So.
How do you think about hoping to ensure that the translation between your formal definition and the actual implementation is sound? I can imagine that is a source of significant problems. I agree, or I hear your point that you made earlier that it's certainly easier to do it than from a prose and a design doc. but I imagine it's still the source of a lot of bugs. Is that true?
Yeah, actually, no. There will always be implementation bugs, and it could be. So in the autonomous testing that or the test cases, the way we generate, it is the concept is similar to refinements, but typically in TLA plus or any refinements, it's like you model both the versions in the high level the same TLA plus language itself. Instead, I'm modeling it the implementation in the real code. Then we have to define some mapping between the model state to the actual implementation. So something like in the model, I have a database with a table which has a status for the transaction. In the model, it would be just a local variable, right? So I need a way to map between these two. So that should be defined. Assuming that is correct, it can test. Okay. The second one is even more easier, which is having an adapter. Like we had an action called checkout. We need an equivalent implementation, and in the implementation, because of the language conventions, or it will also have multiple parameters and all. So we need an adapter for it. So these are the two input from the user. They are pretty standard. LLMs, the adapter LLM created very quickly. Copilot was like without any noticeable input. The translation function between these two states was a little harder. It needed a little bit thought.
So is the end goal, excuse me, is the end goal of Visby to be like someone made a, I don't know, like concert C compiler, or is it just like only for specifications?
So I'm mostly considering it as a specification for software modeling. So code generation is not. I mean, you're asking about code generation later.
Oh no, like concert is like it's a formally verified C compiler
Mm-hmm.
code. So like do you want Visby to like, hey, I wrote a compiler in Visby and it's formally verified, or is it more like specification?
No, it's more. At least currently, I'm thinking only about specifications. Okay, things can change, but I don't know. Because I'm not even familiar with that area of stuff.
I think we are a bit over time already, so we're going to wrap this up. Thank you so much for coming.
Yep.
And thank you for presenting.
Thank you.